Good day, everyone. Our topic for today is about algebra of sets. Now, let us define first an algebra of sets. So, we let X be non-empty set, and then the algebra of subsets of X. This is the notation. We have script A. We use script A because algebra of subsets is actually the family of sets. So it is a subset of the power set of X. This is the power set of X, where this family of subset A here is not empty. So it is an algebra of subsets of X if it satisfies the following conditions. First, if A and B are in the collection or in the family of sets script A, then their union must be in the collection script A. So it means it is closed under the finite unions. Next is, if A is in the collection, then its complement should be in the collection. In other words, it is closed under complementation. Now, let us try to consider this example here. Okay, in this example, we let X be the set with elements 1, 2, and 3. Now, we will show that this family of set here is an algebra of subsets of X. So, with elements or members empty, the X itself here, then the set with elements 1, 2, and the singleton set with element 3. So first condition here, we will try to show that if you're going to get two members in the collection, here A, then its union must be in the collection. So let's have this first. If empty, we will consider empty and X. So empty union X is equal to X. Of course, X is in the collection. Another one, if we have 1, 2, this set, union this set, it is equal to X. Still, X is in the collection. And then, we will try all the possibilities. So, let's do it. So, empty union X is X. Empty union this set is this set. And empty union this set is this set. Here X union this set is X. X union this set is X. Then this set union this set is of course X. It is in the collection. Therefore, it is closed under finite unions. Now let's have here the second condition, that if the set is in the collection, then its complement should be in the collection. So let's have this. The complement of empty is equal to X. So X is in the collection. Let's have X here. Complement is empty. Still, it's in the collection. Now the complement of this set is 3. And the set 3 is in the collection. And then the complement of this set here is of course this set. And as you noticed that every member in the collection, its complement is in the collection. Therefore, it is closed under complementation. Now notice that two conditions are satisfied here. Therefore, we can say that this set is an algebra of subsets of X. Now let's have here the proposition. So we let script A be an algebra of subsets of X. Then, if the two sets are in the collection, then its intersection is in the collection. So let's prove it. So we let A and B be in the collection because because that is our assumption, and then we will show that their intersection must be in the collection. So by the second condition here states that if A and B are in the collection, then their complement must be in the collection. Therefore, the complement of A and the complement of B is in the collection, script A. And then, by this one, the first condition, if we are going to take its union, this union is equal to the union of its complement is equal to the complement of its intersection by De Morgan's law. Still, it is in the collection because it is we are using the first condition, that the union of the two elements in the collection should be in the collection. So hence, since this is already in the collection, we can take its complement, and its complement should be in the collection. So this is the complement of this set here, which is equal to A intersection B. It's in the collection. So we have shown that the intersection of A and B is in the collection. So we're done. Now you can try to investigate using the example given a while ago, wherein if we are going to get any two members in the collection, then their intersection must be in the collection. Now let's consider another proposition here. It states that MT and X are in the collection. Now notice in our definition of algebra of subsets of X that it is not empty. So there should be at least one element in the collection. So in this proposition, we will show that MT and X are in the collection. So let's prove it. Since from the definition again, it is not empty, so we can pick an element from the collection. So by the second condition, if we pick an element, say for example A in the collection, then its complement should be in the collection. That is by the second condition. Thus, if we are going to get the union, that is by using the first condition, take note the union of A and its complement is equal to X. And by the first condition, the union of two members in the collection must be in the collection. So that's why we have this one. Now, by the second condition, because we now know that X is in the collection, so if we get its complement by the second condition, it's still in the collection. So take note the complement of X is empty. So we're done proving this proposition. Next, let's have here an example. So we know that this is the power set of X. What do we mean by power set of X? It means that it is the collection of all subsets of X. So since it contains all the subsets of X, then if we will try to get two members in the collection and then we will get its union, then the union is in the collection. And also, if we are to take the complement of every member in the collection, the complement is also in the collection because it contains all the subsets of X. Now you can try that one by using the example given a while ago. So you will get the power set of x and then show that the two conditions are satisfied. So we can say that the power set of x is an algebra of sets. Actually, it is the largest algebra of subsets of x with respect to set inclusion. Now let's try to have here another example. Empty and x is an algebra because if we are to take the union of this, it is x. So that's for the first condition. Then for the second condition, we will take the complement of every element here. So the complement of empty is x, and the complement of x is empty. So this set is an algebra. Actually, this is the smallest algebra. Next example here is this script L here with members closed and open, close open or close-open interval. So we have closed A and then open sub B, where A and B are real numbers and then A is less than B. Now why this is not an algebra? Because if you are to use the first condition, we are to get the union of the two sets here, two intervals. The union is not in this form. It should be na, if you are going to get the union of the two sets, it should be in this form. But as you can see, they are disjoint. So it is not in the collection. Now, let's have proposition 2.21. Let script A be an algebra of subsets of x. And we have the sequence of sets in script A. We have A sub n. Then there exists a sequence B sub n of sets in our algebra of subsets, such that the pairwise intersection is empty for m not equal to n, and if we are to get the union of the sequence A sub n, it is equal to the union of the sequence B sub n. So let us try to consider this illustration here. Say for example, this script A here is an algebra of sets. So with members A1, A2, and A3. Say we have these sets here, A1, A2, and A3. Now, to find the existence of sequence B sub n in script A, we can let first B1 be equal to A1. So in that case, we can let that as this set B1 equals A1. And then for our B2, we can let that as this one. So this set is A2 minus A1, right? So A2 minus A1. And then for our B3, we could have this set remaining, because we need to make sure that they are disjoint sets. So we have here A3 minus, of course, these sets here belong to A1 and A2. So this is the union of A1 and A2. So we are going to subtract it. A1 union A2. Now take note that from this condition here, the proposition B1, B2, and B3 are sets in script A. So this is a sequence of sets. And then the intersection of B1 and B2, we have B1 and B2 is empty, or they are disjoint. B1 and B3 also disjoint, and so on, for m not equal to n. And of course, if you are going to take the union of A1, A2, A3, we have here the union, and it is equal to the union of A1, B1 rather, B1, B2, and B3. So that's just an illustration of proposition 2.21. Now let's proceed to this definition here. An algebra script M of subsets of X is a sigma algebra if it is closed under countable unions. That is, this sequence, if this is the sequence of sets in script M, then the countable union of the sequence must be in script M. Now take note, script M is an algebra. So when we say algebra, from the definition of an algebra, it is closed under finite union. But here, for a sigma algebra, it is closed under countable unions. So if we have here the sequence a sub I, where I is from 1 to infinity, so the union of a sub I from where I is from 1 to infinity is in the collection. In this remark here, it states that if script M is a sigma algebra, then it is closed under countable intersection by using the De Morgan's law. Just like in the algebra rather, but the algebra is closed under finite union, and we have shown that it is closed under finite intersection. So the same thing here for a sigma algebra, because a sigma algebra is closed under countable union from the preceding definition. So by the virtue of the De Morgan's law, it is closed under countable intersection. Okay, let's have here an example. The power set of X is a sigma algebra. Why? It is because power set contains all the subsets of X. With respect to set inclusion, this power set of X is a sigma algebra. Okay, for this proposition, we let X be an empty set, and we have here a collection of subsets of X. Then there exists a smallest sigma algebra, script A sub 0, containing this collection. Now to illustrate this proposition, let us consider this. So this one is the collection of the algebra of sets, where every algebra of sets contains the collection of subsets of X, script C. Now to get the smallest sigma algebra, so we are just to set the intersection of all the algebra of sets, and we set that as script A sub 0. And this A sub 0 here is the smallest sigma algebra containing this collection of subsets of X.